If we want to explore the whole universe, we'd better have a good map. In this lecture, we'll tackle the question, how do astronomers locate objects in the universe? In math class, we learned that a good way to specify the location of an object in 3 dimensions is with Cartesian coordinates. You choose an origin, and then you pick 3 perpendicular directions to be the x, y, and z axes. But in astronomy, we usually don't do that, for the same reason we don't label points on the globe according to x, y, and z. Instead, we use latitude, longitude, and elevation. We use a spherical polar coordinate system. That makes sense for the Earth, because the Earth is a sphere. And it makes sense for astronomers too, not because the universe is a sphere, but because we're trapped on a sphere. For the foreseeable future, we're stuck here on Earth. That makes it natural to use an Earth-centered coordinate system and to extend our concepts of latitude, longitude, and elevation up into the heavens. Our ancient ancestors imagined the sky to be a glass celestial sphere upon which the stars and planets were painted. Of course, this is not physically correct. The stars that we see forming constellations are actually at very different distances from the Earth. But the celestial sphere is still a useful fiction. So let's imagine a giant transparent sphere centered on the Earth, marked with grid lines of latitude and longitude. The latitude lines tell us how far we are from the celestial equator. That's the projection of the Earth's equator up into the sky. And the longitude lines tell us how far east or west we are from the celestial equivalent of the prime meridian. That way, when we look at a distant star, we can read off the star's angular coordinates by seeing where it appears relative to the grid. That leaves only the 3rd dimension, the distance to the star, the celestial equivalent of elevation, which is much trickier to measure, as we'll see. Now, if you become a professional astronomer, you've got to learn these coordinates and the archaic terminology that goes along with them. You'll learn that the center of the Milky Way is at declination minus 29 degrees, right ascension 1 hour 11 minutes east of the vernal equinox. We won't be concerned with that stuff. Instead, what I want to discuss are the physics problems related to how we measure those coordinates. Let's start with the angular coordinates. Say there are 2 stars that happen to be located along nearly the same line of sight from the Earth, so they'll appear close together on the celestial sphere. If they're too close, they blend together and they appear as a single point of light rather than 2. So what determines whether we can perceive the double star? As you might guess, it depends on how good our telescope is. But we can be more specific than that, and it's worth going into detail because the question gets right at the basic dilemma of astronomy, which is that all we have is light. With few exceptions, our only source of knowledge is the electromagnetic radiation that happens to hit the spinning ball of rock we live on. So we need to understand the physics of light. Imagine a telescope as a big lens pointed at a star straight overhead, which focuses the starlight into a tight spot on our camera. If there's another star in a slightly different direction, then ideally the lens would focus its light onto a different spot in the image. So our image would show 2 dots, star 1 and star 2. Problem, though, is that we can't focus light into as small a point as we might like. As we'll see in a moment, the stars blend together when the angle between them, delta theta, is on the order of lambda over d, where lambda is the wavelength of light and d is the diameter of the lens, or mirror, or whatever we're using to collect and focus light. The reason for this inevitable blurring is the phenomenon called diffraction, a consequence of the wave nature of light. Light is an electromagnetic wave, a traveling pattern of oscillating electric and magnetic fields. So we can imagine the light from star 1 as an ocean wave, a traveling pattern of crests and troughs of electromagnetic energy with a wavelength, separation between crests, of lambda. This wave then passes through the diameter d of our telescope. In our drawing, a crest is just arriving at the opening, and then a lens or a mirror responds to that pattern of energy by redirecting it toward a camera. And the energy gets redirected to a different position on the camera if the starlight comes in from a different angle, tilted by delta theta. But if delta theta is really tiny, how could the lens or the mirror possibly tell the difference? The wave energy is smeared out with a spatial extent of lambda. So the telescope still sees a crest filling the opening. The optical system responds essentially the same way as before, directing the energy to the same spot on the detector. As we increase delta theta, at what point do the waves from star 2 start to look different from star 1? It's when you no longer have a crest extending across the opening. The tilt is large enough that there's a crest at one end and a trough at the other end. For this minimum value of delta theta, it's at least possible for the optics to distinguish between the two waves. Let's do the math. The distance between a crest and a trough is half of lambda. So from the diagram, we see that the tangent of delta theta min equals lambda over 2 divided by d. Now, in practice, delta theta min is a tiny number. For visible light, lambda is about half a micron, while d is usually a meter or more. So we'll use the small angle approximation. Whenever an angle is small, the tangent of that angle is nearly equal to the angle itself expressed in radians, which in this case means delta theta min is approximately lambda over 2d. That's the minimum angular separation we can reliably measure with a telescope of diameter d. Keep in mind though, this is just an order of magnitude relationship based on the rough idea that we need to tilt the waves enough to get a shift of order lambda across the telescope opening. To do this exactly right, we would need to calculate the diffraction pattern of light after it passes through a circular hole of diameter d. What that more complex calculation shows is that the starlight gets focused into a blob surrounded by a pattern of rings, and the diameter of the blob is 1.22 lambda over d. So if two stars are closer than that, their blobs begin to merge together. That's why the usual definition of this diffraction limit is 1.22 lambda over d. Let me pause here to talk about units for angles. Lambda over d is a dimensionless number. It's a length divided by a length. That means that the angle is being measured in the natural units, or radians. In ordinary life, we measure angles in degrees, with a right angle being 90 degrees and 360 degrees going around the whole circle. I'm sure that's familiar, but did you ever wonder why 360? That turns out to be a tradition going at least as far back as the ancient Babylonians, who used a base 60 counting system. It's also why we divide 1 degree into 60 arc minutes and 1 arc minute into 60 arc seconds. It's all very charming, but it is a nuisance for calculations. It's simpler to calculate in radians, the system in which a right angle is pi over 2, and the whole circle is 2 pi. For example, if we're observing visible light with a 10 centimeter telescope, then the diffraction limit comes out to be 6 times 10 to the minus 6 radians. And if you want, you can convert that to the Babylonian system, as we've done here on the screen. It's about 1.2 arc seconds. To put that into perspective, your eyes probably have an angular resolution of around 50 or 100 arc seconds. And the full moon has an angular diameter of half a degree, or 1800 arc seconds. Since the diffraction limit is proportional to lambda over d, the way to improve our angular resolution is to increase D, build a bigger telescope. And that does work to a point. But in practice, there are lots of other reasons why our images might be blurry besides diffraction. Maybe our lens isn't perfectly polished, or our mirror has defects. And then there's the constantly fluctuating atmosphere, which scrambles the directions of light rays at the level of about an arc-second, even at our best mountaintop observatories. So even with a large telescope, we usually can't achieve the ultimate diffraction limit. That's one reason why we launch telescopes into space, above the atmosphere. Now, let's return to our original problem of locating things in space. We've been discussing the physics of angular measurements, but the really tough problem, historically the hardest problem in astronomy, is measuring that third dimension, the distance from the Earth. Imagine we discover some new galaxy. We measure its angular extent on the celestial sphere, but with only that information, we can't tell if the galaxy is relatively small and nearby, or if it's huge and billions of light years away. Let's draw the situation. We're on the Earth, and there's an object located a distance d from the Earth. The object has a true size of s and an angular size alpha. That is, the rays arriving from the opposite sides of the object have an angle alpha between them. We're going to use the small angle approximation again, because in practice, alpha's tiny. Maybe it's just a few microradians. That means alpha is approximately equal to s divided by d, or equivalently, s equals alpha times d. So it's like I said, if all we know is alpha, we can't figure out s without knowing d. A similar situation arises when we measure the brightness of a source. For a given brightness, we can't tell if the source is intrinsically luminous and very far away, or if it's actually intrinsically faint and happens to be nearby. Suppose the luminosity is L. That's the power, the energy per unit time that the luminous object is pouring out into space. We can measure L in units of watts, for example. And if all that power spreads out as the radiation goes farther from the source. The Earth is far away at a distance of d. So by the time the light reaches the Earth, it's been spread out over a huge sphere of radius d. And we can't measure L directly. Instead, we've got a telescope with a certain collecting area, and we measure the power that's received by the telescope. We can then calculate the power per unit area, which we call the flux, F. From our diagram, F equals L divided by the surface area of the sphere, 4 pi d squared. That's an important equation, the flux luminosity relation. F equals L divided by 4 pi d squared. It's another example of an inverse square law. The flux goes down as the inverse square of the distance. If we measure F, we need to know d in order to deduce L. And we really want to know L, the true luminosity, if we want to figure out what's physically going on to produce the radiation. The message again is that measuring the distance to an astronomical object is a crucial problem that we need to solve. And like any tough problem, it's useful to break it down into manageable parts. We solve it in 4 different steps. The first one is using radar. Build a giant radio transmitter, aim it at a nearby planet, and fire. If you hit the target and your receiver is sensitive enough, you can detect the echo, the reflected radio waves. The echo will be delayed by a time interval, delta t, equals 2d over c, where 2d is the round-trip distance, and c is the speed of radio waves, that is, it's the speed of light. And since we know the speed of light, we can calculate d. With the world's biggest radio transmitters, we can measure the distances to Mercury, Venus, Mars, even some asteroids. That allows us to make maps of the solar system with a precision of a few parts in 10 billion. It's an astonishing level of detail. But unfortunately, this method is limited to relatively nearby objects. you can show that the amplitude of the echo falls off like 1 over d to the 4th power. Try it if you like, using the information in this lecture. So to go beyond the solar system, we need other techniques. We move on to the second step of our 4-step solution, parallax. Parallax is based on simple geometry. Hold out your arm and raise a finger. Now close your left eye and look at your finger and the scene in the background. Then switch eyes, open your left and close your right. It looks like your finger just jumped. That's because your right eye is viewing from a slightly different angle, so it sees your finger projected against a different part of the background scene. That's parallax. And if you measure that shift in angle, as well as the distance between your eyes, you can use trigonometry to calculate the distance to your finger. In astronomy, we take advantage of the Earth's motion around the Sun. We take a picture of a nearby star, then we wait 6 months for the Earth to go halfway around. Then we take another picture. That's like closing your left eye and opening your right eye. The nearby star, like your finger, will appear to have shifted in position relative to the much more numerous background stars. Let's do the math. Here's the Earth going around the Sun in a nearly circular orbit with a radius of 1 AU. Out here is a star at distance d. We need to point our telescope in a certain direction to see the star. But 6 months later, we need to point in a slightly different direction. In fact, as the year progresses, the star will seem to move in a little circle on the celestial sphere with an angular radius of alpha. Using the small angle approximation as usual, alpha is equal to 1 AU divided by d, or d equals 1 AU over alpha. And since we already know the value of the AU very precisely from radar ranging, whenever we can measure alpha, we can calculate d. Now, for simplicity, I drew the star directly over the plane of the Earth's orbit. In general, though, the star will be off to the side somewhere. That doesn't change the basic idea. It just means that the star will appear to move in an ellipse rather than a circle, and the parallax angle is the semi-major axis of the ellipse. And if the star is right on the ecliptic, the projection of the Earth's orbit onto the celestial sphere, it'll go back and forth along a straight line. Let's make another diversion to talk about units. As was the case with the diffraction limit, the equation we just wrote, alpha equals 1 AU over d, works when alpha is expressed in radians. But what if we want to use arcseconds? Well, 1 radian works out to be 206,265 arcseconds. So if we're expressing alpha in arcseconds, the right side of the parallax equation becomes 206,265 AU over d. The tradition at this point is to do a little sleight of hand and define a new unit of distance, the parallax second, or parsec, equal to 206,265 AU. That way, the numbers are easier. d equals 1 parsec divided by alpha in arcseconds. For example, the bright star Sirius shows a parallax of 0.38 arcseconds, so its distance in parsecs is 1 over 0.38, or 2.6. As we saw in the first lecture, the parsec is a handy unit for measuring the distances between stars, and it happens to have the same order of magnitude as the light year. 1 parsec is about 3.3 light years. Parallax is by far our most reliable method for measuring distances to stars. But as the distance gets larger, eventually the parallax angle becomes too small to measure, if for no other reason than the diffraction limit. Right now, our best parallax measurements come from a space telescope called Gaia, which was launched by the European Space Agency in 2013. Gaia measured parallaxes as small as a 10,000th of an arcsecond. That's good enough to make maps of the galaxy out to 10,000 parsecs, 10 kiloparsecs. That is impressive. But to go beyond our galaxy, and there's a lot beyond our galaxy, we need to take another step in the quest to measure distances. This quest is actually a long story, and it's central to the history of astronomy. But I'm going to cut to the chase and tell you the two best ways we have to measure the distances to very remote objects. They both rely on the flux-luminosity relationship that we derived earlier, F equals L over 4 pi d squared. Remember, L is the power that an object emits, and F is the power per unit area measured by Earthlings. So we can measure F, but we can't figure out L unless we also know the distance d. But suppose there were some light source out there for which we already knew L, like a giant light bulb with its wattage printed on the surface, as though when you look at Sirius with a telescope, you could see a label that says 10 to the 29 watts. In that case, you could calculate the distance by rearranging the flux luminosity equation. D equals the square root of L over 4 pi f. Now, stars don't come with manufacturer's labels, but in some special cases, we can figure out the wattage even without a label. Here's an image of a famous star called RS Puppis, surrounded by a cloud of material that was ejected by the star. It's an example of a category of stars called Cepheid variables. Cepheid, because the first known example was in the constellation of Cepheus, and variable because these stars vary in brightness. They pulse. They get brighter and fainter in an endless cycle with a period, the time for a full oscillation, that's typically a few weeks. The important thing is that the average luminosity of a Cepheid can be predicted accurately from the period of the pulsations. This was first discovered by Henrietta Leavitt in 1912. Stars that pulse more slowly are intrinsically more luminous. One reason we know this to be true is that some Cepheids are close enough for parallax measurements, so we can determine their luminosities. And among that collection, we observe that L is linked to the pulsation period, P. A schematic chart of luminosity versus period shows this increasing relationship. So, if we spot a Cepheid megaparsec away in some other galaxy, we can't measure its parallax, but we can measure its pulsation period. We just monitor the flux. We see how long it takes to rise and fall. Then we use the period luminosity relationship to determine L, and boom, we've got both F and L, and we can calculate D. We've just figured out the distance to the galaxy where the Cepheid resides. Cepheids are an example of what we call standard candles, sources for which we somehow know the luminosity. Astronomers love standard candles. An interesting historical tidbit is that Cepheids were what first allowed us to zoom out beyond the Milky Way. What happened is that in 1923, Edwin Hubble spotted some Cepheids in the Andromeda Nebula, which at that time was a subject of debate over whether it was a distant galaxy of billions of stars, or it was some kind of swirly gas cloud or a star cluster that was inside the Milky Way. Hubble used the Cepheids to find the distance to Andromeda, and he showed it was a good fraction of a megaparsec away. Therefore, its angular size of a few degrees corresponds to a true size comparable to that of the Milky Way. Funny thing though, even to this day, we don't know exactly why Cepheids are such good standard candles. There's been a lot of progress, but I think it's fair to say we can't calculate the period luminosity relationship from first principles. Of course, we don't always need to understand a tool for it to be useful. We just need to confirm that it works reliably, but it is a strange situation. Cepheids are these powerful beacons that have been used for more than a century to map out our galactic neighborhood. And yet, what's going on inside the beacons remains an area of ongoing research. With our best telescopes, Cepheids can be seen out to a distance of around 50 megaparsecs. But if we want to go further, if we want to reach out to gigaparsecs, we need to find something else. Ideally, we'd find another type of standard candle, one that's orders of magnitude more luminous than a Cepheid, so we could see it all the way across the universe. Unfortunately, nobody's found such a standard candle. But it turns out there is something equally good, maybe even better, a standard explosion. In the 1980s, astronomers realized that a certain category of exploding stars, supernovae, produce fireballs that all have nearly the same peak luminosity. We'll learn more about supernovae later in the course. For now, just be aware that they're called type 1a supernovae, and they all explode with about the same energy, or at least nearly the same energy. They're predictable enough that if you measure the color and the duration of this afterglow, you can determine its luminosity to within a few percent. And how do we know that? It's because we've spotted type 1a supernovae in nearby galaxies that also have Cepheids in them. Here's a chart showing some data for a nearby type 1a collection. The horizontal axis is time in days, and the vertical axis shows the measured luminosity of the explosion. You see how they all rise to about the same level, with differences that correlate with the duration? The faster the explosion fades, the lower the peak luminosity. So when we measure the rise and fall of flux from a really distant type 1a supernova, we can match the observed duration of the event to one on this chart, and then read off the peak luminosity. That's how we use type 1a supernovae as standard explosions. And their great advantage is that they're as bright as 5 billion suns, bright enough to see even when they happen in galaxies far, far away. They are stupendous explosions. You're probably wondering, what causes them? Well, we're actually in a similar situation here as we were with the Cepheids. We don't know for sure what causes type 1a supernovae. They're almost certainly exploding white dwarfs, as we'll discuss in a later lecture, but the trigger for the explosion remains a topic of active research. What is clear, though, is that they work. We can use them to measure cosmological distances. They are the last step in our quest. Time now to start wrapping up this lecture. Let's summarize what we've learned with 4 equations and a chart. First is the diffraction limit. Even with a perfect telescope and no atmosphere, we can't resolve details on angular scales smaller than of order lambda over d radians, where lambda is the wavelength of light and d is the diameter of the telescope. And turbulence in the Earth's atmosphere usually limits us to about an arcsecond, regardless of the size of the telescope. Next, angular size. If an object of size s is located a distance d from Earth, its angular size is s over d radians. Third is the flux luminosity relation, F equals L over 4 pi d squared. Here F is the flux, the power per unit area that we can measure, and L is the power of the source itself, the intrinsic luminosity. Fourth up is the parallax equation. Over the course of a year, nearby stars appear to move on the celestial sphere in little ellipses with a maximum angular size in arcseconds equal to 1 divided by the distance in parsecs. So, a star 10 parsecs away has a parallax angle of 1/10 of an arcsecond. And finally, here's a chart to illustrate our different methods for figuring out distances to astronomical objects. We call it the distance ladder. Each rung is an order of magnitude in distance, so it's a logarithmic chart, like the ones we saw in the first lecture. The bars joining the rungs are the different measurement techniques that work over that range of distances. Out to a few AU, we can use radar ranging. To go beyond the solar system, we use parallax, which works out to kiloparsecs. That takes us most of the way around the Milky Way. From there, we rely on standard candles, Cepheid variables. We measure their pulsation periods, deduce their luminosities, and use the flux-luminosity relation to get the distance. And that works out to around 50 megaparsecs. That's a nice chunk of the universe. It contains hundreds of thousands of galaxies. But there's more good stuff even farther away. For them, we rely on standard explosions, type 1a supernovae. We watch the light from the fireball rise and fall, deduce the peak luminosity, and again use the flux-luminosity relationship to get the distance. That gets us out to gigaparsecs. For the next lecture, though, we'll retreat back to microparsecs. That is, we'll return to the comfort of our own solar system and come to understand the motion of the planets.